Hello, it's Keith here, and this is lesson 11 of the YQuest series of my 650 assembly programming tutorials. We're going to be looking at the PC Engine today, and you might be thinking you've heard all this before because we've looked at the PC Engine before, but this is the enhanced version of the game. Now, if you remember, previously we were using the Tilemap for graphics, and that meant that the objects could only move within 8x8 sort of blocks, so there'd be very jerky movement. Well, you can see now we have nice smooth movement, and the reason for that is we are now using hardware sprites. You can see here we've got very nice smooth graphics, and obviously we can move much faster and everything looks quite good. So we've changed the code a little bit and we're now using hardware sprites for the graphics. The text is still being done by the Tilemap, but we are now using hardware sprites. Okay, so we're going to discuss today how we've done that and what was needed to make those changes. Now, on the PC Engine, the sprites are 16x16 and our tile graphics were 8x8 before. So we're going to need to make some changes. We're going to need to space them out. And there's a tool here in Sprite Editor, sprites 8x8 to 16x16. And all this does is it moves all of the sprites around a bit and just makes them spaced out so that we can now use these 16x16 areas, and that will work okay. And of course, Sprite Editor can export to the sprite format for the PC Engine. If we go to PC Engine, save PCE sprite here, that will save in the correct format for the PC Engine, which is a little bit tricky if you're looking to make them yourself. But there is some documentation on my website if you're feeling particularly masochistic and you want to make your own sprite code. Good luck to you. I certainly managed it, so I'm sure you can as well. Okay, so let's go over to today's code and let's see the changes that have been made to support the PC Engine. Okay, so here is the PC Engine code, PC Engine YQuest2. Now, the first thing is we've had to make some changes to the common code. The common code has had a few tweaks to support the hardware sprites. Now, a hardware sprite will appear at a position on the screen, and because each hardware sprite is an actual sort of separate layer, we can't show a hardware sprite the same hardware sprite number in two positions on the screen, at least without clever trickery, which we're not doing. So we need to allocate a hardware sprite number to each object that we want to appear on the screen at the same time. Now, the way we're doing that is we've got a function here called set hardware sprites, and this will allocate a consecutive numbered hardware sprite to the object within our object arrays. Now, if I just load up the ramdefs, I think it is, here it is, yep. There was an unused byte previously within the object definitions, and that is now the hardware sprite number. Now, the way I'm defining this is a hardware sprite of 0 is an object that does not use hardware sprites, so it's going to use the old Tilemap. We can do that on some systems that don't have enough hardware sprites. 1 or above is going to be hardware sprite 0 onwards, and a value of 255 we're also assuming to be a Tilemap graphic, and the reason for that is the bullet array resets to 255. So just for convenience, we're considering 0 or 255 to be a Tilemap based graphic. Any other number is considered to be hardware sprites for our purposes. So this is going to initialize those hardware sprite numbers, but we do need to make some other changes to the code to support these hardware sprites. Now, you can see here when we're checking the object drawing routine here at the end of the object movement code, we're checking the hardware sprite number, and if it's over 128 or if it's 0, we're treating it basically as being a software sprite, as I say, the Tilemap. Otherwise, we're using this new hardware sprite do get hsprite object routine. Now, the rest of the changes to the code all occur within the platform-specific module. We're going to go over them now. There's quite a few for the PC Engine. Now, firstly, the sprites use separate palettes for the PC Engine. Now, the code is basically the same here. You can just see that instead of the high palette address being 0, the high palette address is now 1, and that defines the palettes for the sprites. We're actually using the same palette data and the same transfer code as before. It's just a different palette that's used for the sprites, and that makes the PC Engine more colourful, so that's very nice. But our simple little 16 colour game, we just need to initialise both palettes to the same data here, and that will get things done for us. As I discussed before, the hardware sprites with a very different format to the background, so we are defining the tiles in a separate batch. Now, our basic tile patterns, we're going to memory address 1000 in VRAM. The sprites are going to memory address 2000 in VRAM, so we're just using the same define tiles function. And you can see at the bottom of our code we now have some new sprite data just here, and these are in PC Engine sprite format. We've still got the bitmap data here. Technically we don't need it really, I guess. We just need the font. The PC Engine has enough hardware sprites that all of the graphics on screen, the bullets, the enemies and things, are all hardware sprites. On some systems where there's not enough hardware sprites, we have to start limiting things down and maybe just do the player and the enemies using hardware sprites, and you do the bullets in software sprites, something like that. So as I say, in this case, it's actually all being done with hardware sprites because the PC Engine has nice hardware sprites, very good capabilities on the PC Engine. Okay, so we've now defined our sprites there. Now the next change comes at the start of the start level routine. Now we're allocating hardware sprite numbers to each of these objects here. We are starting from Sprite 2. Sprite 1 is actually used by the player object. Where is it? Just here. We are defining the hardware sprite. Now the hardware sprite is going to be hardware sprite 1 for the player. You can see that just up here. But the rest of them are being defined sequentially using that code we saw earlier. So all of the objects are being given a hardware sprite number by this routine. Now there's a change to the blanking routine here. It's checking the hardware sprite number, and if we're using a hardware sprite for this object, then we're using this routine just here, and what that's going to do is it's going to move the sprite off the screen. The X, Y position are being set to 0, which is off screen, effectively making the sprite invisible. Nice easy way of removing a hardware sprite. And we're also doing that in the CLS routine, the clear screen routine. We've got to get rid of those sprites, we've got to move them all off the screen here. So we're positioning all of the sprites off screen here, and that will make them all invisible, and that will do the job quite nicely for us. Now this set hardware sprite function is the thing that's doing the dirty work of actually putting a hardware sprite onto the screen. Now we do need to just discuss how hardware sprites work on the PC Engine. Now the PC Engine uses a special bank of data for its sprite object, which we can't actually directly access. Now it's sort of in a separate piece of the hardware. What we can use, however, is something known as the SATB, the Sprite Attribute Table Buffer. This is in VRAM, and this is just a bank of the same data that the sprites use. We fill that up with all of our settings, and then we push it all to the hardware sprites using a special function. You use function register 13 here, and that just basically DMA copies all the data. So it's not a major problem for us. You can sort of tell yourself if you want that the sprite data is in VRAM. It's as close as it makes no difference. Now each sprite uses a total of 4 bytes, a Y position, an X position, an address, and that's the address of the sprite data in VRAM, and that's effectively bit shifted by 5 bits. So it's not the full address, it's just the top few bits of the address, the top 10 bits. And then we've got some parameters. We've got the palette number, X flip and Y flip, and also sizes. Now you can kind of chain some sprites together, so you can chain 2 sprites together horizontally, and you can chain up to 4, I think it is, vertically. So you can make the sprites bigger than just the 16 by 16. Not as good as the Neo Geo, but it's still very good. I can't complain about the PC Engine sprite capabilities. So those are the settings we're going to need to change, and that's what we're doing just here. Now, as I say, each hardware sprite uses 4 bytes, so we're shifting the hardware sprite number to multiply it by 4 here, and then we are selecting the memory address at the 7FXX range, and that's going to be where we're going to store our data. And then we store the Y position, the X position, the VRAM address, and also the sprite attributes at that location. Now, each of these locations actually stores 2 bytes. These are word addresses. I suppose that should actually say words, because there's actually, even though there's only 4 data addresses, each of those stores 2 bytes. So that's setting up the settings for the new hardware sprite. We've got the X and Y position in 0 page entries IX, IY. D and E is the source data converted for the correct address, and HL is the other attributes. And once we've done that, we're just transferring the data to the sprite definitions here. We're using register 13, and we're specifying our source address just here, the 7F range, and that will actually transfer the data to the hardware sprites. Now if I disable these lines here and I run again, we're going to have quite a bad day. There's going to be no hardware sprites. Now this works fine because that's all software, but now I can't see what I'm doing because all the hardware sprites are not being drawn because the data was never transferred to that actual sprite table within the hardware. So that's what we need to do. Now this set hardware sprite function is used by a new function, doGetHSprite object. Now this is basically the same as the old doGetSprite object. It gets the X and Y position from the currently selected object by the IX register, and it's getting the sprite number, the hardware sprite number, it's calculating the sprite frame, and this has been altered to cope with the memory shifts of the address that we want to work with. As I say, the addresses in VRAM of the sprite data and the address we have to pass to this function are different. It's calculating the X and Y address. It's setting an appropriate palette here, and it's dealing with the layering, bringing the object sprite in front of the background, which is what we want. So all of this is setting up the data, and then set hardware sprite is actually defining that hardware sprite as visible on the screen, and that's what it takes. And that's really all there is to it. Now, I'm hoping if you want to play with hardware sprites on the PC Engine, you'll be able to use my set hardware sprite function pretty much as is, and you can use the rest of the code here as a kind of, you know, an example so that you can make sure you're setting up your palette correctly, you're loading your sprites into correct memory addresses and things like that. Because if you're starting off from scratch, it can be a little bit tricky to get things working at first, but hopefully this will help you out. You can go to my website. I've already done another example on hardware sprites on the PC Engine in the platform specific series, and there's some documentation on the PC Engine page of my website as well as the YQuest page, so hopefully it will help you out and get you going with hardware sprites. Now, if you like what you've seen today, please go to the website and download the source code and also the build scripts and things. Hopefully you can get it working yourself. As I always say, you're welcome to use any of my code in whatever capacity you want, and if you manage to use it commercially, I wish you the best of luck. You don't need to give me credit or anything, I don't care. I just hope you enjoy it. Anyway, if you've liked this video, please like and subscribe. I always have to tell you, if you like the videos, YouTube recommends them to more people. Apparently that's how it works. So if you like it and you click the like button, other people might see it and they may like it as well. And if you enjoyed the video, please think about subscribing. 75% of my viewers don't subscribe, it seems, and it really helps my motivation if people subscribe. I guess I shouldn't be too surprised though, because 75% of people don't watch past the first 2 minutes either, so what can you do? Anyway, if you've enjoyed it, I hope you get some use from it. Thanks for watching today. I wish you all the best with your PC Engine programming. Goodbye now.